Thank you very much for your overly generous introduction. So I believe I have about an hour to tell you about various things about quantum gravity. And so I want to tell you today about why the unification of general relativity and quantum mechanics has been so difficult and have been quite an interesting challenges. And in that context, why superstring theory is important. So, and then holographic principle is something we're going to use. So I will tell you a little bit about that. And then from that, I would like to discuss what's known and not known about quantum gravity. So I understand that there is actually some workshop in quantum information also, and there are people from that workshop. And I understand that in that area, there are some interest in quantum gravity, at least some of the people working on it. So I hope this might give some context of why we, string theorists, are interested in this kind of subject. So first, I'd like to tell you why the unification of general relativity and quantum mechanics has been difficult and interesting. Well, if you ask a particle physicist, this is a standard answer to that question. That is that if you start with Einstein gravity, which is this is cosmological constant, and this is the Einstein-Hilbert term, and coupled to some finite number of matter field, then this system is not renormalizable in 4 or more dimensions. And this is, of course, true statement. But it's only part of the story. And so I want to first tell you what's the main question. So in fact, non-renormalizability itself is not necessarily important. Because, for example, there are many other theories that we study in particle physics that are not renormalizable. For example, this is a Lagrangian of pions. And this has a dimension for parameter f. And that causes this Lagrangian to be not renormalizable. But there is no problem in studying it in certain situations. If we are interested in studying property of pions involving energy less than the energy set by F, in this case 184 mega electron volt, then you can use this Lagrangian and compute many of the physical quantities very reliably. And for example, you can calculate things in a perturbative expansion in 1 over f. In fact, energy divided by f or energy divided by momentum. And each term in perturbative expansion can be calculated systematically and renormalizing finite number of parameters in each step. So you can actually calculate some physical quantity and compare with the experiment. So this actually goes back to the idea of Ken Wilson and the renormalization group and the effective field theory. So pion theory, in his point of view, is a low-energy approximation to QCD, which is the correct renormalizable theory of strong interactions. And in some sense, we all believe that this pion theory can be derived by performing QCD functional integral by integrating out high-energy degrees of freedom while keeping the low-energy pion degrees of freedom freezed, and then derive this effective action. So despite this effective action itself is not renormalizable, the low energy prediction from this Lagrangian, including quantum effect, can be made, and they have been verified experimentally. So non-renormalizability itself is not a problem. So in fact, Einstein gravity that I mentioned is also an example of this effective theory. So just like in pion theory, the Einstein gravity can be used to make a reliable prediction, including quantum effect, provided that energy and momenta are much less than its cutoff scale. So in that case, a Planck mass is a threshold. So for example, Hawking radiation from black hole has been calculated using exactly that kind of action. And we think that a reliable calculation. And similar calculation has been done at the inflationary stage of the early universe. And it predicts the fluctuation of cosmic microwave background radiation, which are experimentally detected and compared with theory. And again, this is done by this type of low energy effective theory. And you can even calculate correction to the Newton potential like this. For example, so this is a Newton potential between the two massive objects. And then there is a classical relativistic correction to this potential, or suppressed by m over r. And then there is 1 over r square correction, which is, as you can see, there is a h bar in it. And there is actually a number, 41 over 10 pi square, that you can calculate. This is a one-loop calculation by just pure gravity If you have matter field, you can add contribution from matter and actually get some other number. So these are calculable and compared with the experiment, although I think that this has not been tested experimentally, but we believe that this is the correct prediction for this type of theory. However, there are issues, and I would like to discuss those issues as we go. So first, in gravitational theory, the situation could be different. In the Wilsonian point of view of renormalization, it is important that you set energy scale or length scale and integrating out high energy degrees of freedom. But in gravitational theory, the metrics are degrees of freedom, dynamical degrees of freedom. So that means that distances can fluctuate in in the high energy scale. So this notion of introducing energy cutoff and integrating high energy degrees of freedom may not always work well. And in fact, there had been lots of debate about a question called firewall of black hole. I will not have time to discuss that during the colloquium. I'll be happy to discuss that in person later. And there are some indications that this kind of puzzle has to do with this point. So second question is this. So in the case of pion, we know that QCD exists. And in fact, QCD is asymptotic free theory. So that means that we believe that QCD is actually mathematically consistent theory by itself. In fact, making it fully mathematically consistent theory is one of the 7 millennium program of Cray Math Institute. And then we believe that pion theory can be derived from it. And in fact, it is generally believed that in quantum field theory, without gravity, you can write down any low energy effective action that whose consistency can be examined by criterion in low energy alone. For example, whether a gauge anomaly can be cancelled or not. And then if you have such low energy effective action, then you can hope that it can be embedded in some ultraviolet consistent quantum field theory. And in the case of pion, this is the case. There are reasons to believe, as I will tell you later, that may not be the case when gravitational degrees of freedom are included. So it's an actually interesting question of whether the given theory in terms of Einstein gravity coupled to matter can be actually included, derived as a low energy effective theory of consistent quantum theory gravity in high energy. So that's the second question. And of course, the third question is that there are questions that you cannot answer or you cannot formulate, you cannot even formulate in low energy effective theory. So for example, if you have a pion Lagrangian, if you just have pion Lagrangian, you wouldn't know that strong interaction is asymptotic free. And for that, you really need to know the QCD Lagrangian, because asymptotic freedom is a kind of physics that becomes visible only at the what's called QCD scale, which is beyond the applicability of pion Lagrangian. So there are interesting questions like that the low energy effective theory cannot answer. And similarly, in gravitational theories, there are many interesting questions like the fate of evaporating black hole, or whether inflation model of our universe can be derived from fundamental principle, or what's the nature of singularity of our universes, etc. So those questions cannot be addressed in terms of low energy effective action. So those are good reasons that we are interested in more fundamental theory of gravity. That theory unifies gravity and quantum mechanics. So let me expand on this second point. So you can ask, is Einstein gravity guaranteed to have UV completion? And in some sense, one of the important things about string theory is that it gives you an existent theorem of consistent quantum gravity coupled to degrees of freedom, which looks like standard model of particle physics. So, well, first of all, in superstring theory, one can compute quantum effects without ultraviolet cutoff to all order in perturbative expansion. And ADS-CFT correspondence, which I will tell you later, give you actually a non-perturbative completion, a definition of the theory under certain circumstances. And its low energy theory contains Einstein gravity. And by compactifying the theory down to 4 dimensions, you can have many features that are common in standard model of particle physics, such as several generations of quarks and leptons, gauge interactions, which include SU3 cross SU2 cross U1 gauge symmetry and Higgs mechanism. All these ingredients are in superstring theory compactified down to 4 dimensions. So this gives you a strong indication that the string theory is giving you an existence theorem of consistent quantum theory of gravity, which include Einstein gravity and degrees of freedom related to standard model of particle physics. But as I will tell you later, that not all low energy effective theory like that can have ultraviolet completion, and there is an idea called swampland. And in fact, in addition to this workshop in quantum information theory, as Andrew said, there is an ongoing workshop on swampland going on here. I will totally ignore a participant of this workshop for my colloquium today. So another special feature of quantum gravity, which I will not have time to mention, but I would like to say just a word on this, is that as we all know, physical world has a hierarchical scale that you have atom, nucleon, and quarks, and maybe string, etc. So as you go to shorter and shorter distances, you'll find more and more fundamental physics. Historically, extrapolation of fundamental physics was going to short distances. But there are some theoretical reasons to believe that this hierarchy of scale will terminate once we complete quantum gravity. So this is another motivation for understanding unification of quantum mechanics and general relativity. That seems to be a very special point in the historical progression toward more and more fundamental laws of nature. So before we move on, I would like to tell you a little bit about a holographic principle, because this will play important role in the second half of my talk. So Stephen Hawking, who just passed away last year, played important role in this. So the Hawking radiation, this is a cartoon of Hawking radiation. So in general relativity, we draw light propagating in 45 degrees upward. And so this is the event horizon of black hole. And then if you have quantum field theory, you have always creation and narration of pair of particle and antiparticle. So Stephen Hawking realized that, well, if one of these particles go inside of the black hole, then the other can come out as a radiation. And he calculated the temperature of this radiation and applied the standard of this thermodynamic relation between temperature and the entropy, and derived the form of the entropy, which turned out to be proportional to the area of the event horizon, as was conjectured by Bekenstein earlier, and fixed a coefficient related to the Newton constant. So this is a very interesting formula. So entropy we usually learn in undergraduate as an extensive quantity. So that means that it should be proportional to the volume of the system. But here we are Hawking found that entropy is proportional to area of the event horizon which surrounds the black hole, rather than the volume of the objects that we are looking at. So this led people like Lenny Susskind, Gerhard Hooft to conjecture the holographic principle that says that if you have a gravitational system, then the degrees of freedom should be located at the boundary of the region, rather than the volume of the interior of the region. So very interestingly and strikingly, this seemingly absurd speculation has been realized and turned out to be correct in the context of string theory. So I would like to, for the benefit of those who have not followed the logic leading to ADS-CFT correspondence, I would like to give you a brief heuristic explanation of this holographic principle in the context of ADS-CFT correspondence. So to do that, however, I need to have a little bit of preparation, and that involves D-brane. So here is another star in the holographic principle, the Joe Polchinski, who also unfortunately passed away last year. So we are string theorists, so we are interested in understanding gravity using strings. And there are two types of strings. One is closed string, which has no end, and open string, which has two ends. So I put red dot on the end point of open string. So you can ask, well, where are these endpoints would be located, where there are various possibilities. So it can be ending on some surface, can be ending on some curve, or it can be ending on some points, right? So you have a variety of possibilities. So each one of them can be interesting. Okay, so suppose you have one of those sheets where open string can end. So then there are processes like that. So suppose you send closed string from the left side of this diagram. So you come in. At some point, one of the closed string point over here can open up and end on this sheet, and then rejoin and come out like that. You can certainly consider such process. And in fact, if you formulate interaction in string theory, then this kind of process is going to be inevitable. So this kind of diagram can happen. So you can have a closed string become open string ending on this surface, but then become closed string again. But if you assume such a process take place, then you have to admit that there is also a process like that. That is that if you have, so this is called wall sheet. This two-dimensional surface is called wall sheet. That is a two-dimensional sheet swept out by the trajectory of string. Rather, just like, for example, if you have point particle and if point particle move in space-time, it makes one-dimensional curve. If string propagate in space-time, it sweeps out two-dimensional surface. So if you assume such surface exists, then you can actually cut this surface in slightly different way and see that now closed string get emitted from this sheet. Or you can also have a process where closed string can get absorbed into the sheet. Okay? So once you admit that this sheet, this red sheet, is where open string can end, then it's inevitable that this sheet start emitting or absorbing closed string. One of the things that we learned in early stage of string theory, and in fact 1974, when Shark and Schwartz, and also Yonea in Japan, discovered that the string theory contains gravitational degrees of freedom. Those gravitational degrees of freedom are in the closed string sector. Gravity is actually part of this closed string. So the fact that this sheet is actually called D-branes, so this D-brane emit or absorb closed string means that it can actually emit or absorb gravitons. So namely that this sheet gravitates. This sheet has masses, or if these are extended objects, this sheet has tensions. So for example, if you have a point-like object, then this sheet can emit or absorb gravitons, so this point has masses. And if you combine them together, they become heavier and heavier and eventually become black hole. This is one way string theorists think about black hole. Black holes are a collection of these D-branes. So since mass or energy is localized on this D-brane because they gravitate, so if we combine them together, they can become black hole. Or in the case of extended object, we call that as branes. By quantizing open string on D-brane and by analyzing the Hilbert space, one can count the number of microstates of black hole. And I actually forgot to credit the people who did that. But one of the important work was done by Andy Strominger and Cameron Buffer, who actually used this kind of open string degrees of freedom right here to count the degrees of freedom of this collection of D-brane. And they actually reproduced, in some cases, the Bekenstein entropy formula. So they actually explained this Bekenstein-Hawking entropy formula by degrees of freedom of open string. And this actually naturally explains the holography, because rather than explaining degrees of freedom in terms of closed string, they explain the gravitational degrees of freedom, which is ending on the D-brane, which in some sense are boundary of this region. So this explains that the Bekenstein-Hawking formula, which is sort of motivating holographic principle, is naturally arising in the context of string theory. So So we learned that physical phenomena on the event horizon of black hole can be described by quantum theory of open string on the corresponding D-branes. So quantum theory of open string does not contain gravity, whereas the gravitational phenomena can be described by non-gravitational theory. Therefore, gravitational phenomena in the black hole can be described by non-gravitational theory. I'm calling this non-gravitational theory because, as I said, the gravitons are included in closed string sector. Gravitons are one of the excitation of closed string. So if you restrict your attention to open string alone, these don't contain gravitational degrees of freedom. So what Polchinski's D-branes shows, and what this calculation by Strominger and Waffer show, is that these gravitational physics, such as Bekenstein-Hawking entropy calculation, can be captured by non-gravitational calculation involving open string. The genius of Juan Maldacena is that he was able to sort of distill this observation and captured it in a very nice set of language involving anti-zeta space and conformal field theory. So he actually took particular limit of this correspondence and showed that gravitational theory in anti-zeta space is equivalent to conformal field theory at the boundary. So this is now called ADS CFT correspondence. So this is a caricature of ADS space, which is a space and time. Time goes in the vertical direction. The Cauchy slice is on this horizontal slice. And horizontal slice is a hyperbolic space. And here I'm using Escher's picture to show that. And so if you use the ADS CFT correspondence, the physics such as the evaporation of black hole by Hawking radiation can be described by a unitary time evolution in conformal field theory. So in principle, this provides a solution to the Hawking's information paradox. There have been lots of interesting applications of ADS CFT correspondence. One is to use conformal field theory to understand physics of a black hole and other gravitational phenomena like this. The other is in the opposite direction, to use gravitational geometric description of gravity to address some difficult question about quantum field theory without gravity. And there are lots of applications. There is a very nice, for example, book by Svir Sachdev, famous condensed matter physicist, and other collaborators are using holography to understand condensed matter system. But I will not have time to discuss those things. So now that I told you about holographic principle, so I would like to start discussing its use in understanding physical system. So since there are so many people from quantum information workshops, so next two slides I'm embarrassed to show, but this is for the purpose of graduate students who may not be familiar with this. So I would like to introduce a notion of quantum entanglement. I think the first idea came from this paper by Einstein, Podolsky, Rosen. The name entanglement was actually coined by Schrödinger, I was told. So here is the idea of entanglement. So for simplicity, suppose you consider this a two-dimensional Hilbert space, HA, and another two-dimensional Hilbert space, HB, and consider their tensor product like that. So if you have actually product state like that, this state has no entanglement. So EPR pair is a particular combination of those two, and these states are one of those states which has very large entanglement. In fact, in this case, the maximum entanglement in this setup. Entanglement entropy is a quantity that quantify the amount of entanglement. And the definition is that if you have any state in this tensor product Hilbert space, first, you take a partial trace of the corresponding density matrix over the Hilbert space B, and then calculate the von Neumann entropy of this density matrix in the Hilbert space A. And you can see that for this particular state, which I call no entanglement product state, entanglement entropy is 0, whereas for Einstein, Podolsky, Rosen pair, entanglement entropy is 1. Here I'm actually using log of base 2. And one of the reasons that this is useful is that if you have any state in this Hilbert space and take n tensor product of them, then if you take n to be large, in some sense you can think this entanglement entropy as counting the number of EPR pair in this particular state. So you can see, in some sense, you can see that you are counting the number of EPR pair for a given state, and that can be that's one interpretation of entanglement entropy. So entanglement entropy has become a very useful idea in understanding holography, and as I will tell you in 5 or 10 minutes, this actually seems to capture a very essential part of how holography works in a microscopic way. So I'd like to explain that. And one of the important steps in our understanding of this interesting feature is the Ryu-Takayanagi formula of entanglement entropy. So ADS-CFT correspondence says that the conformal field theory is equivalent to gravitational theory in ADS. So in conformal field theory, since this is a standard quantum theory, you can define the notion of entanglement entropy. So you can ask, well, what does that entanglement entropy mean in the gravitational system? So that's a question that Ryu and Takayanagi asked when actually I was told when they were having dinner in 2007 or so in Santa Barbara, when both of them were postdoc. And during the dinner, they came up with an answer. And so here is a question. So this is suppose you have a conformal field theory on the boundary. So this is a Cauchy slice of the boundary conformal field theory. You divide the Cauchy slice of the conformal field theory into 2 segments. One is called A, and the other is A bar. And if you have that, then you can decompose the total Hilbert space of conformal field theory into direct product of Hilbert space associated to A and the Hilbert space associated to A bar. Now, this statement is actually not true. You cannot do that, but there is a more precise way of saying this. And in fact, the end result is going to be essentially the same as one would have done in this kind of naive statement. So let me go on. If necessary, we can actually say it in more precise way by saying the right set of words, such as Tomita Takesaki. But anyway, so suppose I pretend that this is a correct statement, that if you have a situation like that, then you can decompose Hilbert space into total Hilbert space into the 1 over A and over A bar. Then we can do the same kind of things as I have done over here, and then define the entanglement entropy, say, of the vacuum state of the conformal field theory. So you can calculate, you can define the entanglement entropy for any state, and in particular the vacuum state. So here actually I'm using the logarithm of base E. So what Ryu and Takayanagi proposed and subsequently verified by many work is that if you, for example, start with a vacuum state, then the entanglement entropy for this associated to this region is given by the area of minimum surface subtending the boundary of this area A divided by 1 over 4g Newton. Okay? Obviously, this formula was motivated by Bekenstein-Hawking entropy and the fact that both entropy of black hole and the entanglement entropy contain the same word. But this turned out to be actually correct guess. And this leads to various interesting insights about how holography works. So let me mention one of them. So reconstruction of bulk space-time. So it is actually it was pointed out by Maldacena himself that if you have a black hole in anti-delta space, so this is actually a Penrose diagram of black hole. So you have a singularity, black hole singularity here, and then you have a horizon here, like here. And then if you have black hole, typically you can analytically continue through horizon, and then you can have another asymptotic region. In the case of ADS black hole, it turns out that you have 2 asymptotic regions, both of which look like a boundary of anti-delta space. So it turns out that the black hole in ADS has 2 asymptotic infinity, and Juan Maldacena proposed, and later many people checked, that ADS black hole is actually dual to thermofield double state, like that. So this is a standard trick that finite temperature quantum field theory uses, the analysis of finite temperature quantum field theory uses, that if you are interested in understanding finite temperature state of particular Hilbert space, say HA, it is often useful to make a double copy of that Hilbert space and consider this kind of particular state called sum field double state in this tensor product Hilbert space. In the finite temperature physics, this technique is used as some kind of trick in doing calculation. But Mardasena proposed that this is actually the state dual to ADS black hole. So if we have such a state, then you can ask what is the entanglement entropy of this particular state between the Hilbert space A and Hilbert space B. Obviously, as temperature goes to 0, the only vacuum state contribute. So then this becomes, there is no entanglement between these Hilbert spaces. So entanglement entropy is going to be 0. On the other hand, if the temperature goes up, then this becomes 1 for finite energy state. So then you have a sum of many states like that. So the entanglement grows. So as the temperature goes up, the entanglement grows. So that's one observation. And if you turn this story into this dual ADS black hole language, then what happens when the temperature goes up? As temperature goes up, the Einstein-Rosen bridge connecting these two sides grows. So it was pointed out by Einstein and Rosen that if you have black hole solution, then there is actually a space-like surface connecting these two boundaries. And in this particular case, you can show that the size of this Einstein-Rosen bridge grows as the temperature grows, in fact, proportional. So it turns out that the size of the Einstein-Rosen bridge is proportional to the strength of the entanglement between the two. So this lets people like van Ramstung to speculate that entanglement actually grows the geometry, just like in this case, Einstein-Rosen bridge. So in fact, this is a very interesting historical fact. I think Juan Maldacena, for example, pointed out that this paper by Einstein, Podolsky, and Rosen pointing out the notion of quantum entanglement, and the paper by Einstein and Rosen appeared in less than 2 months apart when Einstein was at the Institute for Advanced Study. It's not clear whether Einstein realized the logical connection between these two important works, but they seem like in the context of holography, these two are closely tied to each other. Now, coming back to Ryu-Takayanagi formula, oh, by the way, so in this case, this entanglement between these, the reason that the Einstein-Rosen bridge is important, of course, is that the size of Einstein-Rosen bridge is the entanglement entropy calculated by Ryu-Takayanagi formula. So another important feature of Ryu-Takayanagi formula is that it actually has been used to formulate what is called subregion-subregion duality, which is a refinement of ADS-CFT correspondence. ADS-CFT correspondence says that anything that is happening in the inside of antidot space can be described as a state and operator on the boundary of this ADS, using operator and state in conformal field theory. But it turns out that after the proposal by Ryu and Takayanagi, more refined notion of holography was realized by many people, starting Hamilton, Cabot, and Lifshitz, and leading to Haley, Dong, and Halo. And so the idea is the following. So suppose you have some region A on the boundary, and you draw Ryu-Takayanagi surface. Then there is actually a sub-region in the bulk sandwiched between Ryu-Takayanagi formula and region A. And these people realized that any phenomena that is happening in the gravitational theory in this shaded region can be understood by state and operator localized in this region A. And you don't have to know what is happening in the complement of the region. So there is some kind of refinement of holography. It turns out that this is so this has been tested in many ways, but this has led to some puzzle. And I would like to tell you about the puzzle and its resolution, because it's going to become important in the second half of my talk. And so this is called the Reconstruction paradox, that the fact that the physics in this shaded region can be described by this region A led to the following, at least two paradoxes. One is this. So please excuse me for my childish drawing. But suppose, let's pay attention to this black cross region over here. So this can be included in this blue shaded region, and therefore described by operator and state on this region, or in this red shaded region, and therefore described by operator and state in this region. So the same physics over here can be described by different sets of operators. So is there a unique description of this physics, or is there some ambiguity there? There is also a puzzle like that. Suppose you are interested in what's happening in the middle of ADS like that. But then divide this boundary into this 4 segment. Then for this segment, you can understand the physics in this region, but nothing else outside. Similarly here, and similarly here. So that means that what is happening over here can be understood by none of these regions. This is a puzzling, because the boundary is described by conformal field theory, which should satisfy the standard axiom of algebraic quantum field theory. And according to that, then any operator on the boundary can be described, can be generated by local operator on the boundary. So if they are not, if this phenomena cannot be described by operator in this region, nor operator by this region, nor operator by this region, nor operator by this region, then what operator describes this region? So that's another puzzle. So there are 2 puzzles. One is that there seems to be a non-uniqueness of the description, and there seems to be no way to describe this physics. So it seems contradiction that on one hand, there is no operator that describes this excitation, and on the other hand, there seems to be more than one way of describing it. It turns out that there is a very nice, beautiful resolution to this paradox. And it was pointed out by Almheri, Don, and Hero, and expanded by a paper by Hero alone, which is that actually the local excitation in the bulk is encoded in the entanglement information on the boundary conformal field theory. And the way that the entanglement is, this information is encoded, make use of particular quantum error correcting code. So rather than, so for example, in this particular case, the information here alone cannot tell you about this state. Information about this region alone cannot tell you about this. Information about this region alone cannot tell you about this. However, if you combine information among these 3 regions, then in fact, the Ryu-Takayanagi surface for these 3 regions is this. So therefore, this entire region is covered by this combination of 3 boundaries. So even though each one of these 3 regions cannot tell you about the state over here, but combination of the information of these 3 regions can tell you about this. And I hope that quantum information physicists here would recognize that this is very much like how quantum error correcting code works. Quantum correcting code is an idea that you can duplicate a Hilbert space and then encode the information in the duplicated Hilbert space in a redundant way. Since you have quantum non-Xerox principle, you cannot make copy of the same state, but you can encode information in the entanglement between these copies of Hilbert spaces so that the information is robust. Similarly, in this case, information over here is spread over these 3 Hilbert spaces. So therefore, even if you compromise information here, it's safe because you can decode the information from these 3 Hilbert spaces. So that's how it was found that that's how holography works, and there seems to be close connection between this and the quantum error correcting code. And this idea has been explored very much and has been very fruitful in understanding holography, and I hope it might also be useful in quantum information theory. So let me finally apply this kind of idea to the gravitational theory. So I'm participating in this swampland conference, so let me actually first tell you what swampland means. So this term was coined by Coulomb-Buffer. So here is one way to ask the question. So given the effective theory of gravity, how can one judge whether it is realized as a low energy approximation to a consistent quantum theory with ultraviolet completion? such as string theory. So one of the non-trivial constraints you cannot see in the low energy effective theory. As I said in my introduction, so in the standard quantum field theory without gravity, you expect that you can write down any low energy effective theory that's seemingly consistent within low energy physics, and then hope that it can be embedded in consistent quantum theory of gravity. So I'm going to tell you that this may not be true in gravitational theory. So first, let me give you an example of that. And this has to do with symmetry. And of course, symmetry has been very important in physics. And on the other hand, symmetry can be deceiving. So for example, well, of course, we know that physicists know that there are two types of symmetry in nature. One is a gauge symmetry, and the other is a global symmetry. Global symmetry acts on the Hilbert space. Gauge symmetry does not act on Hilbert space. But as such, gauge symmetry can be actually ambiguous. For famous example is a duality. So for example, in Zyberg duality, you can have two seemingly inequivalent ultraviolet physics with different gauge group that can lead to the same infrared physics. And in the case of, in some other cases like N=4 supersymmetric Yang-Mills theory in 4 dimension, seemingly different gauge symmetry can describe exactly the same physical system. So gauge symmetry can be ambiguous. On the other hand, global symmetry is well defined because it acts non-trivially on the physical Hilbert space. But I would like to tell you that consistent quantum theory of gravity does not have global symmetry. So this is one of the standard arguments using a black hole. So the idea is that suppose you have a global symmetry G, such as SU2, for example. So then, so if you have continuous symmetry like that, there is actually arbitrarily large Hilbert space that is realizing that symmetry in an irreducible way. So for example, in the case of SU2, you can consider arbitrarily large spin representation. And the problem is that problem with having such symmetry is that it may not fit into black hole, because black hole has a Bekenstein-Hawking entropy. So you can consider the following situation. So suppose you have a charged matter, and you combine them to make black hole. So you have a black hole with large global symmetry charge, like SU2 spin. And let it Hawking radiate. Well, since it's global symmetry, so there is no photon that mediate the charge. So you can expect that Hawking radiation is neutral with respect to the charge. So black hole shrinks. So then you can get into the situation where black hole becomes so small, so the Bekenstein-Hawking entropy, the dimension of the Hilbert space expected from Bekenstein-Hawking entropy is smaller than 2J plus 1. So what happens? You are supposed to have a representation of SU2 with dimension 2J plus 1. And if the Bekenstein-Hawking entropy predicts that Hilbert space is smaller than that, that seems to be contradiction. So this is a good argument. There are loopholes in this argument. And also that this does not exclude discrete global symmetry. So Daniel Harrow and I came up with some better argument. So Harrow and I, so this is a paper we published last year. One is a short summary, 5 pages. And the other is a 35 times larger paper where we describe the complete proof. And then, so by using ADS-CFT correspondence, we showed that if you assume ADS-CFT, the bulk gravitational theory cannot have global symmetry, either continuous or discrete. And then there is also things called the completeness hypothesis. That is that there must be physical state in every irreducible unitary representation of gauge symmetry in the bulk. So we proved those theorems in the context of ADS-CFT. So let me briefly tell you the idea behind ADS-CFT. So if you actually are interested in proving that the continuous global symmetry does not exist, then we don't need this slide. This is just to show that the idea works in the case of discrete symmetry also. So we had this, we learned this from Ed Witten, that there is a very nice work in the algebraic quantum field theory, which generalizes Noether's theorem. So if you have a symmetry, then there is a unitary operator acting on the Hilbert space, which realizes the symmetry. So G is an element of group G. Then for each element, you have this unitary operator. So R is a region of the Hilbert space. So if you have actually reasonable quantum field theory with some technical assumption, then you can prove that for any symmetry like that, if you have actually a union of some region, this joint union of region, then the operator acting on, symmetry operator acting on that region is a product of operator acting on each one of these regions. If you have a continuous symmetry with Noether theorem, this is an obvious statement. Because in that case, what happens is that U of G is an exponential of integral of Noether charge density for this region R. So if this region R becomes sum of this joint union of various regions, then integral of Noether charge becomes sum of integral of Noether charge density. So therefore, if you exponentiate it, it becomes product. So for continuous symmetry with Noether current, this is an obvious statement. But it turns out that for a large class of quantum field theory, this is also a true statement for discrete global symmetry as well. So we assume this. And then use this entanglement wedge construction I told you before, which is that information over here is encoded in the information in this region. And if you make use of these two statements, then we can prove the non-existence of global symmetry in one slide, which I'm going to do right now. So here's an idea. So I'm going to show that with contradiction. So suppose, contrary to our claim, that if there is a gravitational theory in ADS that has global symmetry G, then there must be a bulk local operator that transforms faithfully into another local operator at the same point. So this seems to be a reasonable assumption. So then suppose you have that operator located at the center X here. And then suppose you divide the boundary into these segments. And for this, each segment you have Ryu-Takayanagi surface. And then for each one of these, this shaded region is controlled by this region R1. Now, symmetry, one of the features of symmetry generator, which I pointed out in the previous slide, there's this general Noether theorem, is that if you have symmetry and the generator, and if the region is divided into subregion, then the symmetry generator is a product of symmetry generator associated to each one of these regions. So that should be the case in this case. But then each one of these operators only covers this shaded region, so commute with this operator. So that means that the entire symmetry generator would commute with the bulk operator. So this contradicts with this assumption. So this proves the theorem. So since there are quantum information people, I'd like to note that this might remind you of Eastern Knoll theorem. And in the case of continuous symmetry, this is very similar to Eastern Knoll in that Eastern Knoll theorem says that basically there is no quantum error correcting code that is totally faithful that commute with symmetry, continuous symmetry. So that means that you cannot encode information over here distributed over Hilbert space like that in such a way that the symmetry acting on each of these can be symmetry acting over here, right? So this is Eastern Knoll theorem, but in our case, we actually it applies also to discrete symmetry as well. So this is very satisfying, but it's not totally. It doesn't answer all the questions. So we prove that there is no global symmetry, but it doesn't tell us how symmetry is broken or gauged. And we also proved the completeness theorem that every finite dimensional representation must be realized, but we cannot actually predict how heavy such states are. So it would be nice to strengthen this kind of statement to cover those. So in fact, there are actually conjectures that give partial answer to this question. So I'd like to go into the regime of, so far I have only told you about something we can prove. But now we are entering into the territory of conjecture. So I have given this colloquium a couple of times at various universities in US, and I ask audience whether they can recognize this person.
Always time.
Thank you, yes. So you're the first person who answered. So he seems to like to live dangerously. So I took this photograph when we were together in Aspen this winter. We use his invention every day. Well, every weekdays, I guess. So now, by now, we have a landscape of swampland conditions. So I told you about the no global symmetry theorem and the completeness hypothesis. And there are so many of them, so I organize them into in terms of two measures, quantifying them in two measures. Horizontal axis is from useless to useful, and the vertical axis is rigorous to speculative. And so no global symmetry is a rigorous theorem now, I hope, in the context of holography. But for reasons that I can tell you, it's totally useless. And the completeness hypothesis is somewhat more useful. But then there are other conjectures with various degrees of speculation. And just like everything else in our life, these things tend to lie on the diagonal axis. And so the hope is that we can try to bring this into this corner. And that's one of the things that we are doing in this conference. So I'd like to tell you a little bit about the rest of swampland conditions. So first, let me tell you about this line. So weak gravity conjecture. Weak gravity conjecture is based on the observation that gravity seems to be the weakest force we know in nature. And so this conjecture, in fact, weak gravity conjecture seems to answer some of those questions. So I mentioned that no global symmetry theorem does not answer the question of how symmetry is broken or gauged. And completeness theorem does not tell you how we can bound the mass of lightest charged particle. And weak gravity conjecture, in some sense, is an attempt to quantify this. So here is a conjecture. In any low energy theory described by Einstein gravity coupled to Maxwell field or any massless Yuan gauge field coupled to finite number of matter, if it has UV compression as a consistent quantum theory, there must be a particle with charge Q and mass M such that this inequality is satisfied. So this was conjectured by Al-Qani Hamed, Motor, Nichols, and Buffer. This was motivated by black hole physics, but for me, most importantly, it's true in all known construction from string theory. And recently, there have been lots of intriguing connection between that and the cosmic censorship hypothesis. The Coulomb-Buffer will talk about that tomorrow, I understand. So given this, actually, Coulomb and I, and this is the kind of question people often ask, and we formulated as a new conjecture, which is that there is this equality here. And we need this equality. The only reason we have this equality is that there are actually examples. So in the case of supersymmetric theory, then there are BPS states, and BPS states sometimes saturate this inequality. So we conjecture that is the only case, that in all other cases, this equality should be removed. So that's our new conjecture. And then it has led to various consequences. The one of which is that Anchorita space must have supersymmetry. Otherwise, it's unstable. And in fact, in the case of Anchorita space, it's a very dangerous statement. Because in the case of flat Minkowski space or De Sitter space, even if you have a slight instability, you can have finite lifetime. But in the case of ADS, because of this funny causal structure, even slight instability will kill you instantly. So I can tell you why if you're interested. So this turned out to be actually true in all known construction. In fact, I'm running out of time, so I don't have time to tell you about detail. But after we wrote this paper, for example, I got various emails from various friends saying, how about this example and how about that? So we answered most of them, except one that was pointed out by Harvey Rial. So they had this example where in M theory you can have this ADS space, ADS5 plus CP3. And this has no supersymmetry but seemingly stable. That there seems to be no obvious instability mode. So actually, my student, Lev Spodnyenko, and we looked into that. And we found that actually there is a very interesting instability mode due to some instanton effect. And this generalizes Witten's Karuza-Klein instanton to higher dimension. So unfortunately, I do not have time to tell you about that, but I just wanted to mention because he might be applying to postdoc soon. So another interesting feature is that if you assume this, actually this rule out certain type of neutrinos. In fact, under some assumption about physics beyond the standard model of particle physics, it turns out that if you assume our strengthened version of weak gravity conjecture, then we can argue under some assumption on physics beyond standard model that the neutrino should be Majorana, and then also it was pointed out by Luis Iwagiez and the collaborator that it leads to a very interesting bound on the mass of a neutrino, that the sum of absolute value of mass of a neutrino raised to the power of 4 is bounded from above by the dark energy density of the universe. So it's a very interesting phenomenological fact that the expected value of the mass of a neutrino and the dark energy density of the universe are actually of the same order. So why? So it seems like this strengthened version of weak gravity conjecture, followed by the analysis by these people actually here, leads to an explanation of this interesting phenomenological fact that these two mass scales are closely related to each other. So I'm actually only have 3 more minutes, so let me discuss the remaining conjecture. So there is a thing called distance conjecture. And well, so Daniela and I proved the no global symmetry theorem. And it turns out that the way we prove the theorem applies to spontaneously broken symmetry also. So in fact, we cannot have even spontaneously broken global symmetry in quantum theory of gravity. So this actually is very important because in some version of inflation model, they make use of scalar field which with almost flat potential. So if you have a scalar field with almost flat potential, there is an approximate shift symmetry. So you can shift the value of scalar field and the Lagrangian remains invariant. So that's actually spontaneously broken symmetry. You can think of a scalar field in that case as something like a Goldstone field. And, but our theorem says that that symmetry should be broken. From phenomenological point of view, from the point of view of inflation, it would be interesting to know how it is broken, in what way, and in what scale. And the distance conjecture attempt to quantify this type of question. So in string theory has no free parameters, as you may know, that all parameters in the series can vary locally and their expectation value of some scalar field. And distance conjecture is about the property of moduli space of such scalar field. And metric for that space is given by the kinetic term. And in fact, there are, again, some earlier work in the context of action about some difficulty in actually making the action moduli space larger than some scale. And so we Coulomb-Buff and I formalized this in the following set of conjecture, that moduli space is non-compact. So that means that if you pick any point, you can go infinite distance away from that point. But if you try to go large distance larger than the Planck scale, then the low energy effective theory at that point breaks down. But in a particular way, in a way that tau of light particle with mass exponentially small in distance start emerging. So, and then low energy effective theory breaks down at that point. So this is sort of explaining in somewhat quantitative way how the shift symmetry can be broken. And then it has been a lot of tests of this conjecture. I think at this conference also there are several interesting talk about this subject. And but it's important that it actually is false for non-gravitational systems. That if you take the limit when gravitational coupling goes to 0, then actually you can construct many counterexamples. So this statement is intrinsic to a gravitational system. So this is actually closely related to more speculative de Sitter conjecture. So this is motivated, and I guess Tom will talk about de Sitter space in the afternoon. But there has been many attempts to derive de Sitter space from string theory, and there are many serious attempts. KKLT construction is one of them. In fact, KKLT is one of the best attempts so far, and also the most scrutinized attempt so far. And again, I only have 1 more minute, so I cannot discuss the pros and cons on KKLT construction, but there have been difficulty. One of the difficulty has to do with what's called the Dine-Zyberg problem, which has to, again, to do with the fact that all the parameters in string theory are expectation value of some scalar field, one of which is a dilaton. And this makes the digital space to be particularly difficult to construct. So this let us mean the Coulomb buffer and George Opiedo, who is there, and Lev Spodnenko, and then refined further by Elan Party, who is there, and Gary Xu and Cameron and I, to formulate this type of conjecture for the potential for scalar field. And one important thing I would like to tell you is that the distance conjecture and digital conjecture does not by itself exclude inflationary scenario, but put non-trivial constraint on inflation model. So for example, this is the analysis done by Calisi and Irene Valenzuela. At least Irene is here. And then this is done by my colleague at IPMU. So digital conjecture and distance conjecture leads to various observable statements about the scalar tensor ratio, this is called R, of the inflation. These are important values because these values can be probed by astrophysics experiment in the coming decade. In fact, IPMU, which I'm the director of, is one of the proposers of a Japanese satellite project called LightBird, which measures the B-mode polarization of cosmic microwave background radiation. And there is exciting news that JAXA, which is the Japanese version of NASA, just approved the launch of LightBird in 8 years. So this is going to be the only CMB satellite, B-mode polarization satellite in the coming decade. And their aim is to test the cosmic inflation, at least a single field large variation slow roll models in this way. So there is this, this graph is a little bit too complicated, but this purple line is what LightBird is trying to look at, and compare with other experiment on the Earth. You have the very wide angle, so you can look up the small angular momentum regions, where foreground from a galaxy can be avoided very much, distinguished very much. So this is a nice region to look at, and they strive to go down to R goes to 0.01, which is actually, interestingly, very close to the bound that is given by these conjectures. So it's going to be interesting to find out. So I think that this kind of observation is very interesting, and it is my hope that the string theory can work harder, like with this conference that we are having right now over here, to make more precise and sharper statement derived from string theory before these people either falsify or verify inflation models. I was at the Strings conference, Strings 2019 in Brussels, and Nima Al-Kami Hamed said in his talk that you string theorists lost the opportunity 5 years ago when BICEP made the announcement of B-mode polarization. At that time, you guys should have been prepared to come up and say that no, it cannot happen in string theory. So we'll have yet another opportunity, so I think it would be good to be prepared for that. So this is all I wanted to say, and UV-IR connection may imply surprising infrared prediction on observable phenomena from UV completion of quantum gravity. So, by the way, we are having Asian winter school every year, organized jointly by Korea, Japan, China, and India. And this winter, we are having that in Tohoku University. The application is out, is open until the end of this month, and there are lots of interesting talks. As you can see, string theory takes quantum information theory very seriously, and Michael Walter, who is one of the young, exciting practitioners, will give sets of 4 lectures on this subject. So thank you very much for your attention.
So thank you very much for this very nice talk. I'm sure there are some questions.
So Hiroshi, suppose I invented a technicolor model with some quarks and so on, and I found that the pseudo-Goldstone boson potential had a dip in it, like the one you showed in your picture. Would you say that the de Sitter swampland conjecture rules out that model?
Well, so I think that when we first proposed this, we didn't list this second inequality.
Yes.
And so even the standard model Higgs contradicted with this conjecture. So in your technical model, with this additional condition, is this still problematic?
I'm not sure. I think we could construct one.
Yeah, okay, well, it's interesting. I'd like to know that. So even with M-Planck suppression, is this dangerous? So the technical is dangerous in that situation?
I see. Maybe with that, possibly.
Okay, well, I would like to know that. In fact, if I can exclude technical in this way, it's very interesting.
No, I think by making the techniquark masses small enough, you might be able to get that right-hand side as small as you want.
Oh, okay. That's very interesting. Okay. Please tell me more about that. Yes.
For the various proofs of the no global symmetries,
yeah.
Do they epsilon, like, can you have approximate symmetries, or how rigid are they in terms of approximation?
Oh, yeah. So this is something that is very interesting. So our statement, that the one that Daniel and I proved, is about exact global symmetry only, and so we only use the exact version of Eastern Knull theorem, for example, and you can ask, well, is there approximate statement you can make, right? So that's very interesting. So in quantum information theory, there are approximate version of Eastern Knull theorem, and then. Would that be related to weak gravity conjecture? Well, I don't know. It's interesting speculation. So in some sense, weak gravity conjecture is a sort of strengthened version of this statement in a case when symmetry can be gauged. And so you can ask, well, could there be some variation of this type of derivation? And in fact, we have been thinking a lot about this type of ideas. So I don't want to go too much into detail because this is something I'm thinking about right now. But yes, that's very interesting. So the potentially there are lots of ways to generalize this, and there are lots of ideas in quantum information theory that can be useful in that context.
Just two short comments or questions, basically. I mean, you had the comments about the distance conjecture, yes, that the tower comes down. I think one should make a quantification there, right? So far, the evidence is it comes down in asymptotically large field space distances. I mean, right. The tower could start with a large initial mass hierarchy. And then when the first state comes down, this can be much further out than, say, a Planckian distance, finitely larger, but not larger. Also, I think the statement that the EFT breaks down, like if you have hundreds, thousands of states that have come down below the scale where your original effective field theory lived, then you can speak of a breakdown maybe. But it comes one state after the other.
Yes.
And if each state comes with, say, 2 Planckian distances, and then further, then, having like a finite distance, 3 more states, I wouldn't call this a breakdown. I would call this a modification of your EFT. So
I think both statements, I think I agree that I should have qualified that these are all asymptotic statements that we are making. Yes. And in particular, I mean, breakdown, as you said, if you have some state at the Planck scale, then at that stage, it's not clear whether I should call it breakdown, but you have to modify it. The original effective field theory did not have that degrees of freedom. So it's again, it's a question of where you put the UV cutoff, for example. Mm-hmm. Yeah, I agree.
Okay, so if there are no more questions, let's thank Hiroshi again for this inspiring talk.